So, now if you look back, we can see that there are 3 proof procedures we have developed: calculations, informal proofs and the resolutions, but all of them are semantic in nature. They first assume that there is some truth defined in it, because in calculations you need equivalent substitution. So, which is semantic in nature, which needs first truth or falsity, then you can see what is equivalence. Same way resolution needs first CNF conversion, then you can do whatever. And informal proofs, they will also need substitutions, equivalent substitutions, because the laws you are using in the informal proofs can be used only with the help of equivalent substitution and uniform substitution, right. So, what we want is a completely different procedure rather than the truth. We want to play a game with symbols without knowing what truth is all about. Then we want to develop a proof system from that. Of course, it should be going hand in hand with the semantics, with the proofs should be going parallel to the truth or falsity, that we have to see how it can go parallel. Say in usual mathematics proofs, both the things are mixed together. You know that certain things are true, you take that as a theorem. Then while proving you use axioms, some axioms have been there, so use them and continue. So, now you wanted to demarcate between these two, because we want to study each of them separately. So, once we do not do it, it will be difficult to study them, that how much input we have from the truth, how much input we have from the rule playing activity, right. So, we want to define only certain rules and follow it now. Truth we have seen how it matters, fine. So, what is usually done is you think of some axioms, as in geometry for example, you have certain axioms of Euclidean geometry, then certain inference rules are given, you apply the inference rules, go for deriving the next theorems without knowing what a line is, right, what a point is. Lines and points are defined intrinsically by the axioms or the postulates, because the way you think a straight line may not be that straight. You can have another model where the lines are not straight, that may be possible, we do not know that, right, while developing the axiom system. Of course, we have certain things that our lines are like this, they are straight, points is one point there. So, these are only intuitive concepts we want to formalize. Here similarly we have the concept of truth, but we want to capture it by a rule playing activity, fine. So, it will have certain axioms, it will have certain inference rules, then starting from the axioms, applying the inference rules, you will be deriving some other things, and those will be the theorems. Now, as we go along, we should see that the theorems should be our valid propositions. Similarly, the axioms must start from the valid propositions, inference rule must be one of the laws and so on, but then that is only to make it parallelly going with the semantics. If you do not want that, say you assume something which is unsatisfiable as an axiom, then apply whatever inference rules you have from the laws, then you would get every proposition there. So, that may be useless, fine. So, you want to start with something else, and then we notice something which will be important for us, that all the connectives are not required. So, we can minimize the number of axioms in certain sense. So, we do not want to overburden our memory. Okay. So, you know that there are many truth functionally complete sets like not or, that is enough to express all the other connectives, not and, that also expresses all the connectives. We have not discussed NAND and NOR, by those two are only truth functions which are by themselves truth functionally complete, all the other connectives can be expressed by them. So, here we want to take one such truth functionally complete set, and if necessary introduce other connectives later, right. So, these two will be taking us not and implies. Not and implies should be adequate, right, because or can be expressed through not and implies, therefore, not and or are there in our system and that is an adequate set. So, it will become adequate, fine. So, we will not have even the bottom and top symbols, we have only the propositional variables, not symbol, implies symbol. With that you apply your PL rules, the grammars, and generate all the propositions. Okay. So, till now truth has not come, we have to be observant, very observant there. Nowhere we will be concerned with truth at all, we will just play a game with the symbols. Okay. So, once we take this, that we have the propositional variables, and then we have the punctuation marks, okay, and then we have the connectives. This is our alphabet now. So, from this alphabet we are going to generate all our propositions by following the same grammar or rather similar grammar, because we do not have the other symbols. So, it is a fragment of PL we are concerned with only those two connectives. Then we have to give certain axioms. So, we give our axioms. First axiom is A implies B implies A. So, if you use the semantics, you know that it is a valid proposition. Okay. Invariance, hypothesis invariance, that is our law. So, next axiom we take as A implies B implies C implies A implies B implies A implies C. This again we know to be distribution of implication, fine, but slowly we are not going back to the semantics. So, we forget whether they are laws or not, it is only for our reference that yes, they were laws. Then third axiom we take as not B implies not A implies not B implies A implies B. This is also law of contradiction that we know. So, these are the only three axioms we are concerned with. First two, there is no negation symbol used, but we have the negation symbol. So, we will again assume the third one. These are the three axioms. So, when you say it is an axiom, it does not say that always you have to use A symbol. A, B, C, these are our variables there, they can be replaced by any proposition. So, in fact, they are axiom schemes. Okay. Once you replace these symbols by some propositions, you get an axiom. The same thing also followed everywhere else. When you say x plus y equal to y plus x, so this means x and y can be replaced by any real numbers there. Suppose for the real number you are telling this axiom, fine. The same way we are taking these as axiom schemes, and we have only one inference rule, which is let us write axioms here. So, they are axiom schemes, and we have the inference rule which is MP. MP stands for modus ponens, which says from A and A implies B, you can derive B. Now, see, we are not using the entanglement sign even, because we do not want to go back to the semantics here. Okay. All that we say that if you have A, if you have B, then also you have if you have A, you have A implies B, then also you have B. So, in the sense that suppose you are writing a proof, so you will say A is there, A implies B also has been obtained till now in the proof, then you can write B next. That is what it says, right. Is it clear? So, let us see one example of a proof. How does it look like? Okay. Now, this itself is a proof. Yes, because I have that as an axiom, so I stop there. I say I have already got something, yes it is an axiom, so I have got something, but then I can have something else. This is also axiom 1. Is it okay? Yeah, I have this as A, this as B, this as A. So A implies B implies A. This is also axiom 1. Okay. Now I apply modus ponens. So I obtain this, R implies P implies Q implies P, brackets are the way it is given, fine. So now can you tell me what is the proof in this axiomatic system? We are not reducing anything, we are rather starting from the axioms. Well, this is an example of a proof. In fact, only the middle column is the proof, the other things are just for readability of the proof. We are documenting them so that we can read them. Okay. Can you see that? These line numbers and this documentation only helps us to read that how, why it is a proof, that is all it says. Okay. Not only in this axiomatic system, in any axiomatic system this is the case, that a proof is only a finite sequence of propositions, okay, where each of the propositions is either an axiom or is derived by using some rules of inference given there. Here we have only one rule of inference MP, which uses two propositions A implies B, therefore we have to spell it out exactly. So a proof is a finite sequence of propositions where each proposition is either an axiom or is derived by an application of MP from earlier two propositions. Okay. That is what the definition of proof will be. So in this axiomatic system we have to say in this axiomatic system, we rather give a name, we will call it propositional calculus. Okay. Let us call it propositional calculus. So in PC a proof is a finite sequence and so on, that will be our the concept of proof. So let us write it, a proof in PC, or sometimes we say PC hyphen proof. A proof in PC is a finite sequence of propositions each of which is an axiom or is derived from earlier two propositions by an application of MP. Is it clear? So what is a theorem in PC? So what you obtain is a theorem, right? So it is the last proposition in a proof. So, that will be our definition now. It looks funny, but that is what we are doing. So, a theorem in PC is the last proposition in a PC proof. Okay. So, now our basic concern is just to derive theorems. We go on deriving theorems by following this rule. That is all we will be doing. Fine. So, now we can say that R implies P implies Q implies P is a PC theorem. Okay. So, if W is a PC theorem, we have to develop some symbolism. If W is a PC theorem, a theorem in PC is also written as PC theorem. We write it as okay. So, we have to develop some symbolism. Earlier we are using two parallel lines here, only one parallel line we will use. This is called the turnstile. We will read it as W is a theorem. Okay. So, sometimes we write PC here to say that it is a theorem in PC, but if there is no other axiomatic system, we just write this symbol. So, we just write W is a theorem. Okay. So, this proof which we have done in example 1 says that R implies P implies Q implies P is a PC theorem. So, once we use this along with other symbols, this will have the least precedence, whatever is there to that it qualifies. So, you may not have brackets here, it is easier to read the with brackets, but without brackets also we will read this way, that the whole thing that follows, that is a theorem. Okay. Fine. We will prove a very simple thing first, so that P implies P is a theorem. Okay. Now, question is how do we proceed? Which axiom we start with? We have to start with axioms anyway. If only two propositions are there, then you can use MP, otherwise you can't use it. It requires at least two propositions to be used, exactly two. So, if there are more, then two you choose and apply wherever it can be applicable, but in order that it is applicable, they should be in this form. There is one proposition, a proposition, this arrow sign, another proposition. Even you may not read that arrow as implies now, we do not know what is that. Fine. It looks consistent with our implies of the semantics of PL, of propositional logic, because these are the laws, these were some valid propositions, and this is also a valid consequence, that we know, but its counterpart in semantics or in propositional logic, not here anymore. So, now how do we proceed for showing that P implies P is a theorem? Which axiom we should use? Well, let us take axiom 1. What does it say? Axiom 1. See, always we have the target P implies P. Fine. So, to say that P implies P would come in a derivation, I should take both of them as P, right. I cannot take the whole thing as P, there is one implies sign, in P there is no sign. So, let me say P implies P, then this axiom would be looking like P implies P, right. So, let us start with, so P implies P, it would look like this. This is axiom 1. Now, I can use only MP, nothing else is there. So, if I use MP, because I am interested in P implies P, I have to eliminate this P somehow. So, in MP you have A implies B, then A is eliminated, you get only B, right. provided you have already A. So, we should have already P somewhere, it does not look like I can get P, from which axiom I will get P, it can be any proposition also, right. Where from I will get P itself, I do not know where from I will get. So, this attempt really fails. Let us see which other axiom can be helpful. Okay, let us take axiom 2. Where can P implies P come? So, we know that A implies B, then A somehow can be eliminated and B can be obtained, that is our only inference rule, that is a constraint that also helps in thinking. So, here what I want, P implies P. So, that means the last implication can be obtained if everything else can be eliminated, right. So, this A implies C should be thought of as P implies P now, whatever this B may be, right, if I at all use axiom 2, fine. In that case, how the axiom will look like, both A and C are P now. So, I say P implies B implies P implies P implies B implies P implies P, that is how it will look. Axiom 2 will look like this, if I substitute both A and C as P, B I am keeping at free, I will substitute later whatever is required, fine. Now, in order that I get it, I should have got this, I should have got this, apply MP twice, fine. This I can get, this is A1, P implies B implies P, that is A1, fine. So, I can eliminate this portion by introducing A1 before it. So, now scheme is I start with this as A1, this as A2, fine. Then I get P implies B implies P implies P, fine, by modus ponens, some improvement is there. Now, the thing is I want only P implies P. So, I have to eliminate this P implies B, P implies B I have to eliminate. Well, B is free, B has not been substituted by anything. So, what I should substitute in place of B, so that it will be an axiom, yes, P implies P or Q implies P, any other Q also will do, does not matter, right, because that is also an axiom, fine. So, what we have to do is replace everywhere here in all the 3 lines B as Q implies P or as P implies P, is that okay. So, that means this should be P implies P, this should be P implies P, this should be P implies P, this should be P implies P. Is that clear? Then I can introduce P implies P as A1 and I get P implies P, it is already there if you have, so you do not have to introduce, okay. Is that okay? This is how it will be proceeding now. So, can we complete the proof?
That's semantics to all the theorems which you get. Won't all of them be valid?
What is it?
Like all the axioms are valid if you apply semantics. So, wouldn't that also mean that all the theorems, if you apply semantics to them, it will be valid?
Possibly. And we need a proof.
Asking, is it
we need a proof for it.
Yeah.
We will do that after we get some experience with the proofs. And I would rather ask the other question. If I have something valid, can you show that it is a theorem in PC? Right? Well, both the questions we will tackle later. Okay. So, where we are now? We wanted to show P implies P. Our plan is to start with P implies P implies P implies P. This is axiom 1, fine. This is what the first line reads there, P implies P instead of B. Okay. Then we take from this A implies B implies C, we go for axiom 2. So, that says P implies P implies P implies P, the whole thing implies A implies B implies A implies C. This is axiom 2, fine. Then we use modus ponens to get this, which is P implies P implies P implies P implies P, which is 1 2 modus ponens. Next we introduce the axiom P implies P, which is axiom 1, right. Next I get P implies P by using modus ponens on 4th, 3rd, okay. That is the end of the proof. Fine. So, what it says is that constructing a proof is not that easy, it is not mechanical even, but checking whether a proof, a suggested proof is a proof or not is mechanical. Once you write some proof like this, something, and you claim that it is a proof, we can easily verify whether this is really a proof or not, fine. So, the concept of proof or the notion of proof is effective. There is an algorithm to check whether something suggested as a proof is a proof or not, but to construct a proof is not mechanical, it is not effective, right. It looks like that, we do not know whether it will be or not, okay. So, we have to develop some our intuition to create some more proofs, okay. Let us take one more proof. Again wait for some time, you will see why we have chosen these 3 axioms, why not others. That is a good question, but wait for some time to get the answer. First have some experience. Okay. How do we show that R implies P is a theorem? That is the question. See why he is asking that, he is thinking about our example 1. In example 1 we had shown that this is a theorem, this we have proved to be a theorem in example 1, okay. How did we prove? We started this as an axiom, then this implies R implies this is also same axiom A1, then we used MP. Now, instead of this axiom, suppose I will use P implies P, okay. Then how the proof will go? So, it will start from, where from it will start? It will start from P implies P implies R implies P implies P, or you may start from P implies P directly, okay. Suppose I start from there, that is what example 1 says. Instead of the axiom I am taking P implies P now. Next step you would get R implies P by modus ponens, okay. Is that right? Now, how to make it a proof? It is not yet a proof, it is our rough work, fine. How do I proceed? Well, we have already proved P implies P. So, bring that proof and insert it here. Okay. So, I have now 1 something is starting, that line number was how much 5 in example 2. So, 5 I get P implies P, right. So, bring the proof from example 1, example 2. Up to this you take the proof of P implies P. Next you add them. Here it is axiom 1, here it is 5, 6 MP. Okay. So, proofs of earlier theorems can be used as proofs, can be inserted anywhere. So, P implies P if you have proved, then P implies P can be used later, right. But this leads to another question. If I ask you to prove P implies Q implies P implies Q, what will you do? What will you do now? Exactly, that is what. So, go back to example 2. So, in the whole proof wherever P is coming, you substitute P implies Q there. So, you get another proof. No, just look at this proof, what we have done here, the rough work. The same way we will be doing the rough work for P implies Q in mind instead of P. Look at the fair proof. Here what you do? Instead of P you take P implies Q, okay. Implies P implies Q implies P implies Q implies P implies Q. That is axiom 1.
But axiom 1 can be used only for either proposition or theorem. Proposition is derived already.
No.
For any proposition.
In axiom 1 says A implies B implies A, where A, B are
proposition. Any proposition.
It is an axiom scheme. So, any instance of that is an axiom. Substitute anything for A and B, that is axiom 1. So, I substitute P implies Q for A, I substitute P implies Q for B also, then also I get one axiom, right. So, instead of B taking P implies Q, I will take P implies Q implies P implies Q, that is still alright, that is also axiom 1. Okay. So, what it says is that if you have already proved P implies P, then you can use that as a theorem scheme. So, each theorem is a theorem scheme now, just like your axioms, they are axiom schemes, each theorem is a theorem scheme. So, to give a proof of this, what we should do? It says that you take the proof of P implies P, there you substitute everything, every occurrence of P by P implies Q. So, instead of doing all those things, we will just mention this way, we will accept it as a proof. P implies P, already a theorem, right. Now, substituting you get this, but all these steps will be taken together instead of writing all these things. We will simply write P implies Q implies P implies Q is a theorem, already we have done it. So, we can refer back, for example, example 2, that is where we have proved it, since each theorem can be taken as a theorem scheme. Okay. But the only thing is always you are substituting uniformly, there is no equivalent substitution here, we do not want semantics.
Like one of the axioms is A implies B implies A. What if we substitute for A as P implies P and B as R? I mean, why can't we
Substitute.
Yeah, so then we directly prove this in
Yes,
just
tell.
steps. Why do we have to go through getting P implies P?
You want to substitute, yes,
Or A as P implies P.
A as P implies
P implies P.
P implies P.
Yeah.
So, after substituting what do you get?
I get P implies P implies R implies P implies P.
That is what we had got here. No? You have done with P, you can say P implies P. So, now it will tell us P implies P, it will be something like this. Okay, does not matter.
So I can take as maximum directly. I don't need.
Then
I don't need to prove 1 to 5 to take this.
Then what?
Need to have a P implies
After
P.
this?
P implies P.
After this?
Oh,
This is axiom 1, fine, but that is not your interest. Your interest is this one only. So, you have to eliminate the first one. There you use P implies P as a theorem. Okay, clear? Yes, just to write it in a shorthand way.
But how do we, I mean, I can just come up with, even without the proof, I know that this is true. P implies P is true by my
No.
knowledge.
There is no truth. Once you say P implies P is a theorem, you should have a proof for it.
Unless we previously written down the theorem proof, we cannot apply it. Right?
Yes. So, it develops systematically, because we have only 3 axioms. From 3 we are going to thousands, maybe infinite. We will see slowly. In fact, it is infinite. Why? Because you take any axiom, A implies B implies A, you can substitute any proposition there. So, that itself gives you infinite number of axioms, which are theorems. Fine. Okay, is this clear? Concept of the proof and how to use them as theorems. So, only this much is enough now. We write it as a theorem, because already we have proved a theorem which is P implies P, and each theorem is a theorem scheme. Okay. Let us take one more example. Yes, now try this. So, it looks that we will be using axiom 3 somewhere, but where exactly we do not know. Okay. So, axiom 3 looks like not A, or let us write not P implies not Q implies not P implies Q implies P. Fine. So, now look at the pattern. All that you can do is look at the pattern, nothing else. Same, we should take same. So, suppose I take same, it looks like this. Now, use this as a theorem, job is done. Yeah, that we have proved already. So, we will be starting with not P implies not P theorem. Okay. Next, not P implies not P implies not P implies P implies P, axiom 3. Next, not P implies P implies P, 1 2 modus ponens. That is the end of the proof. Okay, done. We will go to the next. Now, there is something, we do not know what is the meaning of this, right. We have not defined it at all. So, what did it say? It needs some generalization of the concept of a theorem, of proof itself, because theorems are defined from the proofs. Okay. So, here is a consequence, you have a set and then another proposition, we are using the same symbol as theorem mode. Okay. So, we write that sigma, we have to read it somehow, right. We will say sigma syntactically entails W, because there is no semantics now, the other one is semantic entailment. So, sigma syntactically entails W if what happens? If there is a derivation for it, just like your proofs. So, what is a derivation? It is a proof where you can use axioms or not and. You may use this or that, fine, or the premises in sigma, fine. So, what we do? First we derive W from somewhere, and those somewhere are the propositions which are in sigma. We can also use the axioms, that is bonus, right. So, how to give the definition of this derivation? It is again a finite set of sequences, right, or a finite sequence. So, we say that a derivation for sigma entails W is a finite sequence of propositions, each of which is in sigma or an axiom or is derived or obtained from two earlier propositions and W is the last proposition in this derivation. Okay. So, such a derivation is also called a proof of sigma syntactically entails W. That is also called a proof of sigma entails W. Now, the question is how to prove this. So, as usual, if sigma is a finite set, you can write as W1 to Wn, then you omit the curly brackets as we write here. Instead, it should have been written with curly brackets, we just omit them as a convention. Now, how do we proceed? So, it says that in our derivation the last line should have P implies Q, P implies R, yes. In between we might use P implies Q, Q implies R. It does not say we have to use, is that okay? Just like in proofs you have the axioms, you do not have to use all the axioms, fine, only a one you can use and prove P implies P, that is fine. Similarly, here you do not have to use all the premises, but all that can be used are from sigma or axioms, that is what derivation says. Now, how to proceed? Yes.
Schemes or are they fixed?
Sigma is?
The element of sigma, is that also a scheme or are they fixed?
They are just given propositions, actual propositions. just as in your theorem P implies P. Now P implies P only we know. Once we see that P implies P is a theorem, it can be thought of as a scheme also, right. Here we will come to that later. First let us see whether this holds, how to make a derivation from this. Well, where from it can come, this P implies R. See, here I see there is a premise which is Q implies R, okay. There is also P implies R. I have axiom 2 which has such a pattern. The second part of the axiom 2, just look at it. It says A implies C, A implies B, A implies C, but it is R, R is common, right. With Q implies R and P implies R, R is common. Axiom 2 says first part should be common, right. A implies B implies A implies C, first part should be common. So instead of this I should concentrate on this, right. It may come to something like P implies Q implies P implies R. Once this is given, I can apply this and get this by modus ponens. Modus ponens is there, right. We have only one method. Look at the eliminating the left side of the implication, that is modus ponens. So if it is already there, I can eliminate and come to P implies R, but this I have to prove from the first part of the axiom 2, right. So I should have before it P implies Q implies R, but I have Q implies R. So can I prove P implies Q implies R? Yes, we have seen already in example 1. It is not axiom 1. Using axiom 1 you can prove this, right. So you start from Q implies R, use axiom 1, come to P implies Q implies R, use axiom 2, come to this, use P implies Q, come to Q implies R, P implies R, right. This will be our procedure, okay. So let us start. Our rough work says I should start from Q implies R. So this is a given premise, we will write on the third column as P, it is a premise. Next we want to use axiom 1, so I say Q implies R implies P implies Q implies R, this is axiom 1. A implies B implies A, okay. Next I use modus ponens to get P implies Q implies R. Next we use axiom 2 here, right. So P implies Q implies R implies P implies Q implies P implies R, axiom 2. Next use 3 and 4 to obtain P implies Q implies P implies R, 3, 4 and modus ponens. Next use P implies Q as a premise. Next P implies R is obtained from these two by modus ponens. Is that okay? So now you identify this as your hypothetical syllogism. If you think this syntactic entailment is like semantic entailment, then it is a hypothetical syllogism.